Alright, so what we want to look at today in our next couple of lessons here, our next 5 lessons really, is dealing with exponential functions. Okay? We just finished looking at natural logarithmic functions, both differentiating and integrating. Now we're looking at exponential functions, and specifically the natural exponential function. Okay? Later on, we're going to look at exponentials and logarithmics of different bases. Alright, but we'll mess with that later. So let's take a look at this here. We have the inverse function of a natural logarithmic function, ln of x, is the natural exponential function. And the notation is that f inverse of x is e to the x. Okay? So, and you can see there y equals e to the x if and only if x is the natural log of y. So you can see here the inverse relationship. Okay, you guys know that the natural log is a log base e. And when I have the log base e of something, okay, in this case y, if that equals x, then we saw back in pre-calculus how we could rewrite that where the base of the logarithm becomes the base of the exponent. And because a logarithm gives us an exponent, what it equals is the exponent of e. And the argument of your logarithm is what that will equal. Okay? So the argument, it becomes what it equals. What it equals becomes the exponent, and the base stays the base. It's just the base of an exponential function instead of the base of a logarithm now. Okay, so we looked at doing that last year in pre-calc honors. So we're going to use that here to see that inverse relationship. Okay, and you can see the graph here as well. The natural log has the asymptote at x equals 0, a vertical asymptote. The exponential function e to the x has a horizontal asymptote at y equals 0. You can see that there are reflections across the line y equals x. Okay? So, just for a little bit of extra practice here, let's solve a few equations real quick, okay? A little bit of a flashback, okay? So how would I solve the equation 7 equals e to the x plus 1?
Could you take the natural log of both sides?
Okay, we could take the natural log of both sides. And guys, there's actually 2 strategies to this. I want to show you both. I usually just use what Alex said. We'll take the natural log of both sides. And we're using the inverse relationship here because a natural log will undo an exponential. Okay, and we have here x plus 1 equals ln of 7. And then I subtract 1, and x simply equals negative 1 plus the ln of 7. Okay? You can leave your answer like that. You don't have to write it as a decimal. Okay? Now, if you recognize the inverse relationship, that's good. This is kind of the second option that people will use. They'll either take the log of both sides or the natural log of both sides, but then they will use one of the laws of logarithms, the exponent rule, okay? And they'll say, okay, well that means that ln of 7 equals, and they'll bring the exponent out in front, so it's x plus 1 times the ln of e. Well, what does the ln of e equal?
1.
That equals 1. Okay? That's basically why the inverse relationship works. You don't necessarily have to write that in order to get to there if you just recognize it as an inverse. Okay? Alright, so that's an exponential function. What if we have a logarithmic function, ln of 2x minus 3 equals 5. How would I solve that one?
So you do the base to the power of 5 equals 2x plus 3.
Okay, good. This is a log base e, So 5 is the exponent of e that gives us the argument, 2x minus 3. Remember, the argument's the term for the stuff inside the logarithm.
Could you then take the natural log of both sides?
You can. What would that give us, though?
The original equation.
Yeah.
That would take us back to the original equation, okay? So, you can do it, it just won't help us in this case. At this point, all we have to do is get x by itself. So we add 3, so it's e to the 5th plus 3, then divide everything by 2, and x is going to be e to the 5th plus 3 all over 2. Okay? So just a couple of quick equations here to solve to help us practice. Any questions? Are we remembering how to do this? It's been a little while, but okay.
A little rusty, it is a little oiled, but I'll be okay.
All right.
Mr. Hayton, so
Yes.
why that becomes e to the 5th?
This is a log. The natural log is a log with a base of e. Okay? And when you see a logarithm, when you see this, what that equation is actually telling us is this. It's saying 5 is the exponent,
Oh, I got it.
okay,
Yeah.
of e that will give us 2x minus 5. Okay? Yeah. That's really what that is saying. Okay?
Mr. Dixon, when we're solving such problems, can I just use a shortcut and like say like, okay, e to that power equals ln of that, whatever? Or should I always do the ln of both sides?
No, you don't have to
Not
do
this kinds of problem, but in the example one kinds of problems.
I mean, you can skip a little bit of steps. If it's a thing where it's like saying to show something, like you're trying to prove something, you want to make sure that you show all the steps, for sure. If you're just trying to solve an equation, you know, if you can skip right to, hey, ln of 7 equals x plus 1, that's fine.
Okay.
All right, so now let's actually think about the function itself and then look at our derivative rule, okay? First of all, remember that the domain of a natural log was all real numbers. The range is all real numbers greater than 0, okay? Remember we said it had that asymptote at y equals 0. The function is continuous. It's increasing and one-to-one. We know it's one-to-one because it's the inverse of the natural log, okay? It couldn't be an inverse if it wasn't net one-to-one. And then the graph of f of x equals e to the x is concave upward for the entire domain. And you can see the limit as we approach negative infinity, or the left side, it's going to approach 0. Again, it has the asymptote at y equals 0. As x approaches infinity, our function is going to approach infinity as well. Okay, so those are some basic properties just as a review. This was one of our parent functions we studied back in pre-calculus. But now let's take a look at the derivative, okay? And no, that's not a typo. The derivative of e to the x is e to the x.
What?
Okay? It is its own derivative. Okay? Now, that's pretty simple. Where it gets a little complicated is when you don't have just an x in the exponent. If you have anything other than just a plain x, in other words, we have e to the u, what do you need to use when you take the derivative? The chain rule, okay? So that's why you see here e to the u du dx. Alright? That's our chain rule. Okay? So, as I'm looking at this, it's not just e to the x, so I'm going to have to use the chain rule. So, the u, just to do one completely here, the u is 2x minus 1, so du dx equals, alright, so the derivative is exactly what you see, e to the 2x minus 1 times the derivative of the exponent, the du dx. So that's times 2. Okay? So when you have an exponential function, you copy it down identical to what it is, and then multiply by the derivative of the exponent. Okay? Let's look at an example of another one here. Okay? Here we have e to the negative 3 over x. So u is negative 3 over x, or negative 3x to the negative 1. Alright, so what is du dx here?
3x to the negative 2.
Yeah, 3x to the negative 2, or 3 over x squared. So, the derivative here is, I copy it down exactly as it is, e to the negative 3 over x, okay, times the du dx. So it's times 3 over x squared. And how you choose to write it is up to you. You could write it in front or write the whole thing as a fraction like that. Either way it'll work.
I wrote it in Spanish.
Okay? Go for it. Alright? So, derivatives of exponential functions. Really easy. Okay? So easy even IVSL does it.
Oh.
Ha ha ha.
Oh, first, ouch. Roasted the entire Ivy program.
But they did do it like 2 months ago or so.
Oh.
So,
Now we are.
anyways. Alright. Little AP-IV rivalry humor.
Sounds like Will's. Now we're the scripts.
Alright.